So this afternoon we've got the first session is now we're dealing with mathematics and games, and then after that we're going to have some workshops, and there are going to be 4 simultaneous workshops, and you will see the room on the programme. So I'd like first now to introduce David Wells on my left. David is a noted author on mathematics topics, and he's going to talk about the connection between chess and mathematics. David.
Thank you. That's interesting. I'm not the caller, no idea. I'm going to start by making a brief explanation. While John was talking about one of the worst things that can happen to a speaker at a conference is you realise, listening to a previous speaker, that they've cut in much of what you were going to say, which is extremely embarrassing and potentially disastrous. Listening to Rob Easterway this morning, I had exactly that feeling. I've known Rob for many years, but we didn't consult before this conference, no reason why we should, and I had no idea he was going to say what he did. So I started making notes immediately. I've been scribbling away and adding some annotations to the screen prints I have here to remind me of things that I can say which I wouldn't otherwise have been able to say, because I'm assuming, I hope logically, that you were all here this morning, and so I can assume that you know, you saw, and you heard, and you remembered pretty much what Rob said in his introductory comments. So I'm going to try and avoid saying anything that he said, which means I have less to say, but I should have some extra comments to make, but I have to remind myself of them from my written notes, having a memory like this. So if I pause occasionally to look down, it's not because I've entirely forgotten the plan of things, it's just I'm reminding myself. The connection between chess and maths. If all you knew that was learning chess benefited learning mathematics, you might think, yes, possibly this was a completely empirical result with no theoretical foundation whatsoever. We know that it isn't so. Professor Grabner this morning made clear that from a neurological point of view, there are connections between the very parts of the brain which are active in maths and chess. But there are other reasons for thinking that they are strongly connected. You might almost say cultural reasons. Sorry, I'm just picking up the wrong one, yes. And here are 6 of them. The first is philosophical, I'll say, the second is mathematical recreations. If you consult mathematical philosophers of maths, they tend to be pretty cheesy on the subject of any connection between maths and games like chess. The usual assumption is that maths is vastly superior, which George Hardy pretty much said in his book, A Mathematician's Apology. Chess is relatively trivial and so on. But in fact, there are strong connections. One of the strongest connections, a quite obvious one, is mathematical recreations, which are mathematical, but they're also games. If they're not games, if they're puzzles, then you turn the puzzle into a game by selecting 2 players and just choosing your goal. So mathematical recreations naturally is a crossover between pure mathematics and ordinary abstract games like chess, Go, bridge, whatever. All those games too involve tactics and strategy. And so does mathematics. If you think of mathematics in terms of, say, algebra, you have an equation, you can make a move, you can decide to double both sides and so on. You can think of the moves you're taught in school as being moves in a game, in which case you have tactics and strategy in mathematics as you do in abstract games like chess. And that leads to proof and proving. There is, as any teachers present may know, there's a bizarre movement abroad at the moment in academic mathematics education to make out the proof, which they seem to have suddenly discovered as a topic, is tremendously difficult, extremely obscure, causes pupils endless problems, and therefore causes problems for their teachers. This is total, utter nonsense, I can say with confidence. Proof and proving are not difficult ideas for children to appreciate. But having said that, one of the simplest ways for them to appreciate proof and proving in mathematics is to start with mini-games. And this is where I go back to Rob this morning, where he demonstrated his third exquisitely beautiful example was Chomp, in which the first player must win, the first player having made the top left-hand chomp. Whatever the second player does, the first player could have done first. I suspect, because pupils may well be under the impression, which they may have falsely got from their teachers, that proof is rather difficult, and therefore a proof which is so exquisitely simple may appear to be sort of something wrong with it, but there isn't. And there are much simpler positions in games, as I'll illustrate in a moment, which show how pupils can develop ideas of proof, which is quintessentially mathematical, according to mathematicians, in the context of mini-games. Then, of course, you can be creative. You can be creative within maths and within games to make a brilliant move chess or a brilliant sequence of moves. You need imagination. You need to be creative.
John, chess.
What?
Chess.
There's what's called chess.
An example of that, children can create their own games or modify the rules of existing games, but also mathematics. In a sense, you create games. For example, the 19th century mathematician Möbius had the idea of taking 2 points and calculating, if you like, their weighted average. This is a very simple idea, many children can understand it. But it leads to something called the barycentric calculus, which is a new bit of mathematics, a new mathematical game, if you like. And finally, the last on the list was complete analysis. It is perfectly possible to analyse a game completely in the way that you might take a mathematical problem, a puzzle, and think about it deeply, work out the answer, and feel completely satisfied that you now understand the problem perfectly. Okay. This is also where there's no clock in this room. It's nice to have, it's nice for the speaker to have a large clock on the back wall, but there isn't one. The deep philosophical question about mathematics has always been, ever since the ancient Greeks, what are numbers? What is number 2? On the one hand, 2 is obviously abstract. It's in your head, it's not a solid thing on a table. This is solid. A numeral carved in wood will be solid. The chess pieces out there are solid, but the chess king is not solid. The chess king is an idea. Here is the chess queen and all the moves it can make. The queen is defined by the moves it can make. In other words, the queen exists insofar as there is an object, an abstract object, which actually has those moves. But once you define the queen like that, then every chess player in the world, every child who is competent to understand the rules of chess, millions and millions of adults, and anyone in some distant galaxy who ever played a similar game and learned to play chess, would agree that the queen has a very solid feel to it. It's a psychological fact which mathematicians recognise when they talk about being Platonist on weekdays, that mathematics seems to them to be incredibly real, although it is, in fact, obviously abstract. And so the question you might say is, how can number 2 be simultaneously abstract, which it certainly is, but also have this extraordinary feeling of being concrete and solid? And the answer, in my opinion, though a lot of philosophers won't agree, it's very contentious, there are loads of books on the subject, is that number 2 is abstract and concrete at the same time because it's defined by rules. It's as simple as that. The pieces in chess are defined by rules. Anything defined by explicit, clear rules which are shared is simultaneously abstract and also at the same time concrete. For more details, games of mathematics, subtle connections. And I also wrote a book on philosophy of abstract games, which is on the same thing. So, philosophically speaking, there is a connection between abstract games of all sorts and mathematics of all sorts. And so you might say, well, in that case, since children can certainly play simple games, if they don't play chess, they might play drafts, or any other number of pencil and paper games. And insofar as children can, 1, 2, 3, 4, 5, 6, 7, this connection is natural. It is rather, as Professor Granner has implied, pretty much, a function of the way our brains work. We are able, naturally, to appreciate and understand concepts which are simultaneously abstract and concrete. Just a moment, that's better. Okay, mathematical recreations. This also overlaps with what Rob was saying this morning, because the 3 examples he gave us were all mathematical recreations. The clue is in both halves, mathematical. There's no doubt this is mathematical. Each shape is 5 identical squares drawn full edge to full edge. It's recreations you can play with it. There's all sorts of puzzles. The original puzzles were by Henry Newton more than 100 years ago. You take 12 of these, 5 12 60, fit them into an 8x8 square with 4 squares left over. And his puzzle was to leave 4 squares in the block of 2 by 2. But although this is quintessentially mathematical in a sense, it's also a game. In the 1950s, Solomon Gollum wrote a book about these shapes. He called them pentominoes. Dewey hadn't done that. He named them pentominoes, had all sorts of puzzles, such as fitting them into an 8x8 square, 4 by 16, or whatever. And he also invented Gollum's game, which perfectly illustrates how an abstract puzzle becomes a game. You have a puzzle which is to fit the pieces into an 8x8 square. Tricky, not easy, but there are many solutions, especially with a computer. But what you have to do is say, well, we'll have 2 players, and they'll play alternately, and the goal is to fit in as many pieces as you can, which is the same goal as for the puzzle. But in this case, the player who is the last to fit a piece in is the winner. None of the remaining pieces will fit into the blank squares on the board is the loser. So in this case, this is quintessentially mathematical up to a point, and also it's I was going to say typical abstract game. It's not a typical abstract game. I'll come to that in a moment. There is one respect, though, in which this is not typical of mathematics. In mathematics, we expect to find structure and pattern. There is pattern here on the board. The pieces are strikingly idiosyncratic. They're all constructed by the rule, which delivers 12 of them, provided reflections and rotations are not distinguished. But when you look at the pieces, there's no other pattern among them. And consequently, Gollum's game has never become that popular. There is no book, Fred Blogg's greatest Gollum games, because it's not possible, as it were, to play a beautiful, exquisite Gollum game. All you can do is, forgetting about strategy, there isn't any, I think I'm right, and ask yourself, oh, well, it's down to tactics, and the tactics are awkward, tricky to visualize, you've got these funny shapes, and you just try and look ahead as far as you can. So, this is an abstract game, it is mathematical, but in a sense it's sort of at one far extreme from the most beautiful, brilliant and powerful mathematics. Applied mathematics, partial differential equations, whatever, are absolutely packed with exquisite structures, patterns and relationships, which make them exquisitely beautiful as mathematics, but also extraordinarily powerful in terms of applications to the real world. Right, we move on. And here is Fox and the Hound. This is another abstract game. Very briefly, the fox at the bottom can move in any direction and is trying to get to the top edge. The hound can only move downwards, left or right. The fox starts, the hound play next. If, for example, the fox moves here, hound to here, fox to here, hound to there, fox to here, hound to there, fox to there, hound to there, the hounds have created a nice row, replicating their position here, but one row further up, and the fox has no way through. It's a draw. Once again, this looks more like a real game. It's more like drafts. You have pieces moving in a similar manner, but it's much simpler, and it's completely solvable, but not by, I suppose, small children, maybe by older children. I have to apologise for this, of course. I should have realised that Norse Cross, which was live, was done again and again and again, and chosen something else. I'm not going to explain this. What I was going to say is pretty much what Rob said this morning, by a very simple analysis, by considering whether the next circle move, the north, goes into a corner, which is really duff up here, or into the middle of one of the sides, which can be done in 4 ways, which is the best idea. You end up by north either losing immediately or drawing. It's impossible for north to win unless Cross plays very, very badly indeed. But the point I want to make here is this is an example of proof and proving. If small children, say 7 or 8 year olds certainly, can realise that they can demonstrate in this position that it is either win for cross, or win for 0, or a draw, then they are proving something. Their proof is relatively elementary, because all they're doing is considering some possibilities. A little tree of possibilities, you can either do that or that. If you do this, you can do that or that or that. If you do this, you can then do that. The little tree builds up, but it's not very long. And young children can explore it. They can even draw it in their, Wendy referred this morning to their, was it chess exercise book or something like that? Anyway, a great idea. You have a book in which you record your ideas, and the children are attacking this problem, and their task is to say, Can it be proved or not? The answer is yes, it can, and relatively simply. Creating your own game. I don't have time to talk about this at length either. It's a fascinating game invented by John Conway. In this position, just in case you can see roughly what's happening, football stands for philosopher's football. This is the football. If I was on this side, and it was my turn to move, I would jump over those two, jump over that one, end up there, and I would win. But if this player has his turn to move, he or she would play over there, and they would win. What it illustrates, among other things, is that the pieces are incredibly simple. The white and black pieces are basically all black. There's no difference in that respect. The football is the only distinguished piece. The rules are very simple. It's played on a chessboard, and yet it's extraordinarily tricky. Many years ago, I had the satisfaction, that's the right word, of playing this with John Conway, and I thought I had some idea what I was doing, but in fact I had actually no idea at all. I was totally thrashed, demonstrating that although it might look, a question of a bit of calculation, looking ahead, and then choose your move, it's actually nothing like so simple. As might be said for the next puzzle, this was suggested by John Fleming. Thank you very much. Chess players create problems. Anyone playing an abstract game can take a position or invent a position and find something problematic in it. Just as there are millions and millions and millions of problems in mathematics, including those that I mentioned. In this case, again, I'm not going to explain in detail what happens, but I can tell you roughly. White is to play, and the black pawn on the h5 appears to be running away from him. If he merely chases it, the pawn queens, then the white is hopelessly lost. So what white does, as you might possibly guess, on the Holmesian principle of... I've forgotten the quote, so I'll drop it. White cannot chase the black pawn directly. So white moves to here, and then to here, and then to here. And by the time he gets there, black has a choice. Black can either allow white to catch the black pawn, in which case it's a draw, which is what white's aiming at, or black can decide that he will not let the white pawn queen. Yes, I got that wrong way. White gets to there, and either black decides to stop the white pawn, in which case white stops the black pawn, or both pawns queen. It's a famous study by Richard Rayleigh, mathematics. Right, now we come to an example where I always laughed that down when Rob Easterway demonstrated one of these problems this morning. The point of the corner, any number of squares. The winner is the person who ends up in the top right-hand corner, which might remind you of the squishy soapy square in the bottom right-hand corner of Rob's first two games. And principle turns out to be somewhat similar. Suppose it's my turn to start and I choose to go there. If you know what you're doing, if you practice, you go there. If I do one, you'll go there. If I leap across to here, you will go down to there. And then I realise at that point that whatever I do next, you win. So in this case, the second player wins. If I start in that corner, whatever I do, you can move the rook back, whether I go vertically or horizontally, onto the main diagonal, and you keep it on the main diagonal, and so it ends up on the main diagonal at the end of the game. This game, here we are. This game was, well, in the first place, it was the subject of an article I wrote a long time ago, this is 1988. The subject of the article was 4 games which might be used to help pupils in maths classes to appreciate mathematics better. Shirley Clark was the maths advisor in London at the time. Germaine and Nicholas, by the way, are not the original Germaine and Nicholas, who would now be in their 40s they are 2 young chess players who both played for England. But I like to think if they'd been in the same position as the real Germaine and Nicholas, they would have come up with the same conclusion. What Shirley Clark wrote in the follow-up article was this kind of maths is so exciting for children. Germaine was writing his ideas for new rules. Nicholas was compulsory trying out his own ideas. And then she concluded that the theory expressed in the original article, that this was extremely good for children and so on, had proved to be true. The children moved on to an idea of proof. And what they'd done was pretty much like this. Their written account of it went like this. We were testing to see if the person who played first won. This is a very scientific way of approaching games, but mathematics has not a science in it. As Philip Davis once said, most Euclidean geometry was first discovered by experiment and proved afterwards. Then they go on, as we were testing, we found that if the player moves the rook onto the diagonal line, you will always win. Well, that's true. Now we know this the test is over. If you move first, the other player will win because they go straight to the diagonal line. And the comment bottom right came from Shirley Clark. When they finished analysing the game, they played for some time, a period or 2 periods. When they'd drawn their conclusion and written it up, she asked them whether they wanted to play the game anymore. And they replied very forcibly, no, they didn't, it was boring. The reason it was boring was that they completely understood it. They completely solved the game. That was all there was to it. So this is a very simple game. Much simpler than the games that Rob produced this morning. But similar in a way. You are aiming for a corner square, and the corner square is the key to the solution. The children didn't stop that. As Shirley Clark reported in her article, they immediately started thinking to themselves, not just, oh, this is boring, I want to do something else. What shall I do, miss? I'm bored, I want to go home, etc. They immediately started thinking of new ideas, and they became very excited over this, which I think is a sign that abstract games to children are potentially exciting and fascinating and creative. But partly for the reasons that Wendy again said this morning. The children, as it were, are in charge. They're not just doing what the teacher said. The teacher gave them the game to experiment with, and they experimented. And they drew an extremely logical conclusion. But then, having solved that game, went on to other ideas. Move the rook 2 squares at a time. Use a knight instead of a rook. Start on only white squares. Move the rook in any direction. That's slightly strange. You might wonder how the game's going to end. But they were having ideas, and that is what's important in this context. They don't just play the game you give them, they can think of new games. Chess, of course, has many variants. I don't know of children playing chess who are much inclined to change the rules, which are, of course, extensive and relatively complicated. But it's coming Christmas, it may be that some of you will play Monopoly with the family at home. Traditional pastimes, some families are not identical to those of Parker Brothers when Monopoly was first invented. People do have a tendency to change the rules to satisfy their own particular taste. But that's one of the great things about abstract games. You can change the rules. In mathematics, you don't change the rules just like that, because the, well, let's say elementary arithmetic, and this is why it's so useful in practice, is a model of, let's say, groups of stones on a table or on a beach. So elementary maths is a model of the real world. And in that sense, you can't change the rules just like that. There are deep principles. But on the other hand, as I mentioned earlier, you could invent something like the Mobius and his barycentric calculus, and all sorts of other. There's any number of geometries, apart from the main ones, and so on. So mathematics and abstract games do have that in common too. Children and other people can be extremely creative. Right. Get back to this. I mentioned earlier that Golem's game has no structure. A lot of structures have no structure. It's very easy to invent rules for games or little mathematical things which don't turn out to have any interesting deep structure. You think maybe the rules are surely going to generate some kind of pattern. But then the thought occurs to you, why should they? There's nothing in the rules of the game which tells you what patterns it's going to generate. Chess is a wonderful game and extraordinarily profound and beautiful because the rules of chess do happen to generate structure. The idea that the square in front of an isolated pawn is weak is an example of strategy, and this is a structural aspect of the game which pupils take a long time to learn. This game, which I'm sure you all know so I can explain it, is quintessentially mathematical. It's based on a binary pattern, which can in fact be drawn as an equilateral triangle, divided up into sub-triangles and hexagons, and then every move in the game is represented by moving from one vertex of the equilateral triangle towards another. On a mathematical graph. It's to do with binary because the number of moves required to move those 4 pegs to the 3rd peg is 15, 2 to the 4th minus 1. With 3 pegs it would be 7, 2 cubed minus 1, and so on. So this is an example which contradicts any suggestion. If Golem's game seems, you know, well, okay, it's a game, but, you know, it doesn't compare with maths. No pattern, no structure, no deep results, no exquisite proofs. This is a counterexample. This is just as simple as Golem's game. and does have elegant proofs, beautiful arguments, and simplicity. Okay, finally, top quote is false. I'm afraid David Hilbert didn't really know what he was talking about. He obviously meant that if you do a scratch on a stone, if you're near Neanderthal and that's all you can do, it doesn't mean much. But as soon as you do several marks, or you start doing 1, 2, 3, 4, 5, then they develop meaning. As soon as you have the rules of the rules of the game give the pieces meaning. So chess pieces by themselves, you might find that if you don't play chess, you find a chess king lying around on the floor. You know what it is meaningless to you. You put it in the game with the rules and they become deeply meaningful. So the first statement, I'm happy to say, is completely false. Mathematics and games are extraordinarily, profoundly meaningful. The second quote, which you have read by now, I hope, is true, except for the last word. I do think that the word fun is completely inadequate. It's not inappropriate. There's an element of truth in it, but it is actually false, looking at it strictly. For the simple reason, the satisfaction that players get from playing chess or any other game, mini games, the kind of puzzles that Rob was looking at this morning, or that they get from mathematics if they're properly taught, is far deeper than anything which could be described as fun. I don't know what the word is, but the word fun is, the word fun is definitely the wrong word. So I would urge you, if you see the word fun being used to describe the satisfactions of mathematics, of raising a strong objection and indicating that mathematics and abstract games are indeed wonderful and fascinating and suitable to children, but what they get out of it is not fun. Thank you.